can't really do statistics without probability coming into it. So that's what all of Chapter 5 is about. So the first thing to answer is, well, what is it? If we're going to be talking about it, what is it? If you'll just jot this down, please. This law of large numbers. Can somebody put that in their own words? I mean, this is straight out of the book.
The more times something happens, the more likely it's going to happen.
That's a good try.
It's like the more times you do it, the closer you get to like actually doing something.
Okay, that's getting warmer. Mr. Black?
The more times you do it, you get closer to like an accurate representation of the proportion.
That's right on the money. So let's put it in context. Good answer. Let's put it in context. Say I'm flipping a coin. What's the, just from your, experience, it's a fair coin. What's the probability of getting heads? So every time I flip it, 50% chance it's going to be heads. So let's say I flip it 5 times and they're all tails. Is that possible?
Yeah, it is.
Would that make you go, oh, wait a minute, there's something wrong with that coin? Now, see, would that make you conclude that you're always going to get tails? No. So what this law of large numbers is talking about is saying, all right, just like Carter said, what if we flip that coin 10,000 times? Now then we've got this huge number of tosses. And what would you expect then the proportion of heads to be? Pretty close to 50%. Now, probably was not going to be exact, right? But if we did it over and over and over again, then I would expect that 50% heads is probably pretty close to what's going to turn out. Now, if I flipped it 10,000 times and it came up heads a tenth of the time, I'm going to think something's wrong with that coin. It's not fair. So that law of large numbers. Gambling casinos. Y'all might not have ever been in one because usually you have to be 21. But they've got sometimes these big slot machines or something. And if somebody wins in there, it could be $30,000. And all these lights go off and the bells are clanging. And it's just like, hey, and everybody gathers around and somebody, gets $30,000. Why would they make such a big show out of it?
So people keep playing in.
That's right, because everybody's going to go, well, that could be me next. It won't be. It won't be, because the casinos know the probability of everything. They always win. In the long run, now see, in the long run. In the short run, they just lost $30,000. But in the long run, they're going to make all that back the next hour. So that just keeps people playing. How about insurance companies? They know how many 18-year-olds are going to die in Texas this year. Really, really close. They don't know which ones. So your folks might be getting something in the mail going, hey, buy a life insurance policy for your kid. Well, when you're 15, 16, 17, 18, 20, you don't need life insurance. What are the odds of you not living? You're probably going to make it to your next birthday. The insurance companies know that. And so they're selling insurance policies because they know they're not going to have to pay out the money on them. They know the odds. They always win. So that's the law of large numbers. It's based on tons of repetition. Okay, here's a little bit of vocabulary. Sample space. If I took all the possible outcomes and put them in a bag, that's the sample space. Usually that's abbreviated just to capital S. So look at this one die here. Let's assume it's fair. It's got 6 sides. So how many different outcomes could I get rolling that die? 6. So my sample space would be 1, 2, 3, and so on. It's just a set of things. Those curly braces sort of indicate set notation. So it's a set of values, 1, 2, 3, 4, 5, 6. That's the only possibilities. So let's say event 1 is that I roll a 4. Okay? How many ways can I do that? 1. Right? So there's just one possibility there. I don't need the comma even. How about, bless you, event 2, roll a number less than or equal to 5. Well, what's going to be in that event? Well, 1, 2, 3, 4, 5, right? 6 isn't going to be in there because it's not less than or equal to 5. How about roll an odd number? Those are my possible outcomes. 1, 3, 5. How about roll an odd number that's less than 5? Yeah, just 1 and 3. Okay, so we're doing some fundamental counting here, and some of the later sections in this chapter are going to be talking about specialized ways of counting, when you can't just count them like we just did. Now let's take a look here. Here's, in the end of this chapter, we're basically only going to have 5 rules. Here's the first 2. Any event you're talking about is going to have a probability between 0 and 1, including 0 and 1. So the probability of flipping a coin and getting heads, well, that's 0.5. We kind of assume. Rule 2 is saying, if I took all the possibilities or probabilities in the sample space, they should add up to 1. And that's kind of intuitive, I hope. So I could say, okay, for my 1 coin, the probability of getting heads is 0.5, and the probability of getting tails, and that big P there stands for probability, is that, right? If I'm flipping 1 coin, the only possibilities are heads and tails. And yeah, I know, it could hit on the edge and stay there, but when's the last time you saw that happen? So 1. Again, if I add up all the probabilities, remember they're all between 0 and 1, I should get 1 as a total. We'll talk about it. Now notice something about probability. Is it talking about what's already happened? No. It's talking about something that's either going to happen or not going to happen in the future. If it's already happened, we know whether it happened or not, right? Okay, something I want to direct your attention to, the probability model. When you see those words, what do? You list all the possible outcomes in the sample space and put their probabilities. Just a chart, just a table. Okay, let's keep going. Here is a very colorful jar of something. I'm going to think of candy. I want to make a probability model of this. So I'll give you a second to draw this. So So I'm just listing the colors, and I'm going to go back and count them. So red, I'm seeing, what, 4? Purple, 4. Green, 5. Orange, I'm seeing 1. So total's 14. We don't have a model yet, though. So what's a probability model? It's a list of all the possible outcomes. So in my table, I'm going to have red, purple, green, orange. So now then, how do I get their probabilities? I take the number of them that's there and divide by 14. So this one's probability, red's probability, the probability of red would be 4 divided by 14. And if we round off to 3 decimal places, what are we getting? Y'all have calculators. 0.286. Thank you. So the probability, so here's the color. Probability of whatever here, 0.286. How about purple? That's going to be the same thing. Green, 5/14.
0.357.
Thank you. And orange,
0.071.
thank you. Okay, so if I add all those up, now that's the probability. So what does that mean? That means if I put all these candies in a bag, shook up the bag, reached in and pulled one out, here's a probability I'm going to get each of those colors. If I add all those up, I should get pretty close to 1. So there's 8 and 12, that's 20. 10, 18, 23, 30.
How is this different than just finding the frequency
It's not at this point. A frequency distribution does what? It's giving you a table on stuff that has already happened. This is no different. It's just based on this, what would you expect to get? In other words, if I said, I'll bet you $1 that you don't get orange, would you take that bet?
Yes.
Yeah.
that I don't get? I was thinking about.
Got to be careful when you're playing somebody else's game.
With the you don't get orange?
I
I would not.
No, you wouldn't take that bet because orange, less than 10% of the time you're going to get it. Every time I go in a convenience store, there's people lined up buying lottery tickets. They have no idea what the probability is that they're going to win. My sweet mother used to write down the numbers that had won, and so in her mind, those weren't going to happen again. She had these lists of them. Okay, that's a probability model. This thing up here is a probability model. You've got a list of the possible outcomes and the likelihood of each one of them. So the odds are, if I just reach in there and pull one of these out, I'm more likely to get a green one than I am any other color. Again, it's what's going to happen in the future. Okay, let's keep going. Now, this empirical method, it's saying the probability of an event is how often it occurred based on the number of trials. So this is like an experiment. And this is exactly what Ms. Wiley was talking about. Isn't this a relative frequency kind of thing? Yeah. But it's based on experiment. We're going to do one here in just a minute. Okay, so empirical means by experiment or observation. Let's see, right here, right now, I've got 1, 2, 3, 4, 5, 6, 7. 7 girls. I got 3 guys. Okay, so there's 10 of you in the room right now. If I randomly chose, and I can't do that because it wouldn't be empirical. I'd be thinking theoretical. Let's do an empirical one. So get your calculators, please. There's another method, and this is kind of what we use all the time. This is called the classical approach. And for it to work, each outcome has to have the same probability as any other outcome. So I'll give you a second to think about this. So when we say the probability of getting heads from one flip of a coin, well, how many ways could that happen? 1. How many possible outcomes are there? 2. And so this is the classical approach. We're still talking about something that's going to happen in the future. Notice that contrasts with the empirical approach, which says, let's do an experiment and just see. How many times does it turn out? And down at the bottom, it's talking about just what we talked about in the law of large numbers. The more experiments we do, wouldn't we kind of think that the empirical approach would get closer and closer and closer to the classical idea? That's all that's saying. All right, I've got a family with 3 kids here. You don't need to write this down unless you just want to. Let's work it and then take a picture. Let's do that. What's the probability of, with 3 kids, having 2 boys? So how many possible outcomes are there? 8. So I know now look what I had to do. Notice BBG is different from BGB because the order matters here, right? So these 2 right here are 2 different things, even though both of them have 2 boys. Okay, so we're probability of 2 boys. So there's 2 of them right there. 1, 2, 3. Is that what you're getting? Okay, probability of 3 girls. Well, I know my bottom number is 8. 3 girls. How many have 3 girls? Just 1. Probability all are the same gender. Good morning. How are you? Well, that's good. Probability of 2 of the same gender. We're just counting. 2 of the same gender. So we'll talk exactly 2. So there's 1, 2, 3, 4, 6. At least 1 boy. Now watch out for these at least things. At least 1 boy. 7. No, it doesn't equal anything. We are talking about probability. No more than 1 boy. Oh, here we go. A girl with an older brother. So here's 1, 2, 3, 3 eighths. Am I missing one?
Girl, boy, girl.
Girl, boy, girl. Yeah. So half the time, with 3 kids, the girl's going to have an older brother. It'll be 4 eighths. So what are we doing? This is what? The classical approach. You list all the outcomes. There's only 8 of them. And then you count how many match what you're looking for. All right. If you don't think about it, you go, well, if I'm rolling 2 dice, you forget that, just like back here, you forget that boy, boy, girl is different from boy, girl, boy. Those are two different outcomes. And you might not realize, well, they've got one of these dyes colored black and one of them colored red. So, actually they don't. They just got a thing going down the middle. To really realize what's going on, it helps with their different colors. But we're good. We're good. So what's the probability of rolling a total of 7? I'm rolling 2 dice. Well, how many possible outcomes are there? 36. How many of them are 7s? Well, look what they've got lit up here. 6, 1, 5, 2, 4, 3. 3, 4 is different from 4, 3 here. 2, 5, 1, 6. So 6. So the probability of rolling a 7, you would expect that to happen about 1/6 of the time. How about the probability of 12? How many ways can I do 12? Okay. How about 2? How many ways can I do 2? Just one. How about the probability of a number less than 8? Wow, how many of those fulfill that? Less than 8. Okay, so this whole row, this whole column, less than 8. These, less than 8. Those. So how many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All we're doing is counting. This is the classical method. How many ways could 2 dice come up? Well, 36.
Not 21.
Hmm?
It's not 21.
Yeah, I'm getting 20.
Because it looks like you circled, or you should have circled.
I missed this one. I missed this one right here. Okay. Hey, I only missed by 1. Okay. Thanks. All right. What if I want a committee of 2? Now, the order doesn't matter in a committee, right? I want a committee of 2 from this sample space. So we got Homer, Marge, Bart, Lisa, and Flanders. Okay, he's not a family member, but he's in this group that I'm choosing from. Okay? I want a committee of 2. What's the probability that Bart will be on that committee? How many different committees can I get out of this, first of all? Y'all work this out and let me see what you get. First of all, we're just figure out on scratch paper or in your head, how many different committees could I get? And notice Marge and Bart, Bart and Marge is the same committee. The order doesn't matter. Melody, you already got it? Okay. Okay. 10? How did you get that?
Just put every one together one time. Yeah.
Okay, so I could have Homer and Marge, Homer and Bart, Homer and Lisa, Homer and Flanders. So there's 4. Then, starting with Marge, I can't do Marge and Homer because they already have. So then Marge and Bart, Marge and Lisa, Marge and Flanders. So there's 3. Starting with Bart, Bart and Lisa, Bart and Flanders. And then Lisa and Flanders, the only combination left. Okay, so 10. Good. So I know there's going to be something over 10. So probability of Bart Okay, how many committees is Bart on? 4. So the probability the committee has Bart on it is 2 out of 5. If I put all these names in a hat, shook it up, pulled out 2 of them, the probability Bart is one of those 2 names is 2 out of 5. This is just the basic concepts of probability. We'll pick up more tomorrow.